Hi everyone, in this video I'd like to introduce my solution of a problem B3 of the 76th Putnam competition. So problem reads like this: the set S be the set of all 2 by 2 real matrices, this M given by these 4 entries, in that order form an arithmetic progression. Find all matrices M in S for which there is some integer k greater than 1, such that the kth power of m is also in the an arithmetic progression. So here's an example of a general description of arithmetic progression. You start with an arbitrary number and you add p to get to the next term, and you add the same p to get to the third term, and so on. So if you subtract n plus first term, subtract nth term from the n plus first term, you get this quantity p, which is independent of n you choose in here. So difference of adjacent terms are always the same. So you can call that first entrance A and add b to get the second entrance b there, and c is over here, and you have add another p, so this is plus 2p, and this is 3p. So the matrix they're talking about, which I'm going to call in quote in arithmetic progression, is always in this form. So choosing a and p cover all the matrices they're talking about. So if the matrix is like this, and they're talking about the kth power of m, how can we actually approach that kth power with what we know about m? And if k is getting higher and higher, usually it gets quite complicated. And whenever I see a problem like this, I remember there's this wonderful theorem in Cayley-Hamilton Theorem that allows you to write down any polynomial expression in M, this matrix, down to kind of lower degree polynomial expression. So here's Cayley-Hamilton Theorem, and here's the matrix, and we can think about eigenvalues. Maybe this eigenvalue may be complex, but those eigenvalues, including all those complex eigenvalues, they're all in this equation called characteristic polynomial, and this is obtained by, let me prepare the slide. All right. So the characteristic polynomial is actually the determinant of these 2 by 2 matrix. There's a lambda unknown indeterminate, and I being identity matrix, and subtract m, and the determinant of this one will be polynomial in lambda, and that's what you're looking at in here. All right. So all the eigenvalues in here, it's the zeros of this polynomial, and all the zeros of this polynomial is the uneigenvalues of this matrix M. So what has it got to do with this m to the kth power, which is following in here? This is an equation in number, or expression in number, but if you replace that lambda with a matrix, m squared makes perfect sense. Multiplying this scalar to m makes perfect sense in identity matrix. So you can certainly consider this polynomial algebra for matrix M, and the magic is that this matrix turns out to be zero matrix, which is Cayley-Hamilton Theorem. Not only it works for 2 by 2, but it also works for all square matrix. So we have this wonderful vanishing relation. So if you have not just the kth power, but any arbitrary polynomial in M, you can divide that polynomial, enjoying the coefficient being in a field, and you have a quotient, which eventually doesn't matter, so I use the star in here, and there's a remainder. Since our divisor is in degree 2, the remainder must be degree 1, and because this is a zero matrix, so as a matrix, this expression is equal to x times m plus y times the identity matrix. So this mk can be reduced down to that shape. So actually dividing, it's actually a lot of work, but I think it's somewhat better than actually multiplying matrix in k times. So here I summarize it again, and I'd like to show you an example. Simplest example of these matrix in arithmetic progression is probably p being 0. So I put p equals 0 there. So I got this very simple matrix. Sorry about the interruption. Those phone silence now. And so you go here, and that's the equation from Cayley-Hamilton Theorem. So if you plug in p equals 0, you can see that's 2a in there. So we have this quadratic relation on m. So how can we turn that one to understand m to the k? For example, you can do that m squared is a 2am. So that's pretty simple. What about m to the third? You can multiply m both sides. Then you have m to the third, 2am squared. But m squared is again 2am. So you can replace that m squared here with a 2am. So you end up at 4a squared m. So m to the third is equal to that. This all that thing can be again obtained by that long division process, but if it is special shape like this, just working on the power of m, maybe it's more efficient doing it this way. So I hope you got the pattern. Just keep multiplying 2a in there, so it's whatever, I think is a one lower power in there, something like this. So it gives you an idea on how to use Cayley-Hamilton Theorem. So here is it. I summarize that thing again, but let's go back to our problem, which is about in this matrix being in arithmetic progression. So once you look at this m to the third, m to the third means is a 4a, or actually m squared itself, and here m squared is a 2am. So if you multiply 2a there is a 2a squared, 2a squared, and 2a squared, and 2a squared. If all the entries are the same like that, it was one of the simplest arithmetic progression. So m squared is already an arithmetic progression, so you don't need that the result to conclude that m is one of the kind. So if you raise this one to the higher power, 2 or higher, if that is back to this in arithmetic progression shape, then we call this in S. So this particular one, AAA, is in that set S. So we found one. And realize that after multiplying other matrices, you feel like there's very little chance that something like that's going to happen. So first you think maybe this is it, and try to show all the other things is not possible. But you soon realize by playing with this Cayley-Hamilton theorem, you realize that that wasn't it. There was actually more. So I looked at this characteristic equation and realized that I actually got this equation by just setting p equals 0. So I was thinking, what if I make this 2a plus 3p equal to 0? In that case, you got this nice, very simple quadratic equation as well. So if you turn that around, if you multiply m is m cubed, and here multiply m, you have 2p squared m. So you end up like that. So again, if you multiply 2p squared to m and see if that's back to arithmetic progression shape. So let's actually work that out. And in here, if you multiply 2p squared and 2ap squared, the 2p squared multiplied there, then here is a 2ap squared, and 2p squared multiplied there is 2p cubed. So let's skip that rest of the calculation, and by looking at, just assume that this is correct, and just understand why this one is back in S. So here's a 2ap squared, and to get to that, you add 2p cubed. And if you add 2p cubed again here, then you have 4p cubed. If you add 2p cubed again, then you get 6p cubed. So this is in arithmetic progression. So we found another one. Anything that this 2a plus 3p is 0 in that form in here, and this third power is in arithmetic progression. And we're thinking that, okay, that's the nicest one that you can pull out by using these two ideas and making these two coefficients 0. Then you may think maybe really this is it. And the next attempt is to actually show that thinking is correct. So let me rephrase the question again. S is the matrix matrices M. So the M is in arithmetic progression, and some higher power M of M is also in arithmetic progression. Then collection of all M such that P, either P is a 0 here, or 2A plus 3P is a 0. So when I wrote down this condition 2A plus 3P in a more constructive, a parameterized way. So A and P are real numbers. So any real number that satisfies this equation can be parameterized with M like this. So I parameterize like that so that I deal with integer coefficients. So the first one, P equals 0, if you plug in P equals 0, the matrix look like that. And I wrote it like this immediately. And I realized, oh, this is really scalar multiple of this matrix. It's an abstract vector. So that's one motivation that I'm going to use later. So when 2A plus 3P is 0, A and P are parameterized like this. So if you plug in there, you get these numbers. Let's check. A equals negative 3M. If you add these two, you get negative M, and so on. So M are common, so you factor that out again. All the second kind is also written as a scalar multiple of this matrix, which is we're going to look at as an abstract vector. So our thinking is that probably this collection is it. There's no other who have that property. Right, I realized the pointer was not working, so there was some frustration for you to follow, but it's back on. So let me pick up from here. So there's just these two matrices I found, and I'm trying to show these two are all. So I was already expressing these two sets and in linear algebraic terms, a span with the real scalar. And like that, it's one-dimensional space. I looked at this M again. I realized we can also write that as a linear combination of the two abstract vector. Those are two matrices, this one and that one there. So I separate with this A's in it and P's in that, and you can see this is true, and this is one vector and second vector, and these two are, as a vector, is linearly independent. Therefore, and all these matrices in arithmetic progression is actually inside these span of dimension 2, span of these two linearly independent vectors. So I thought I really like this setup. So I further realized, and then I'm going to play a little bit of linear algebra in here. So my first vector is 1, 1, 1 that came from A part, and B came from the common difference part. And when you raise this to a higher power, you end up at multiplying these two vectors. So I calculated here, and I is the identity matrix. And we would like to look at this as 4 abstract vectors in the vector space of matrices. And I'm going to skip the following calculation, but it is a fairly elementary calculation that should show that these 4 matrices are linearly independent over the real coefficients. So if you consider span of these 4 matrices, they have dimension 4. And I'm going to call that vector space R, but it is also an algebra. If you multiply these two matrices, you end up at matrices can be expressed as a linear combination of these 4 matrices again, which is not absolutely clear because I don't have a B times A here, but you will soon see B times A is still there. So if M is in arithmetic progression, that means M is in linear combination of this two vector A and B there. So our goal is that if M is expressed like that after you raise it to the kth power, can you get back to V again? So that question was phrased like this. After trying actually raising to second power and third power and so on, I realized it, and this is really good idea to introduce this simplification. These complex expressions can be actually handled a lot in a simpler way, and that's the idea of this projection map. So if you have that element in that span, linear combination of the four things right here, my first projection, pi 0, is just picking up the last element, the I component, which that's what I'm going to say, I component. And the second projection, if you have any expression like that in terms of basis, then it's going to pick up AB component. So I'm going to call that one I projection. This one is an AB projection. And using that, you can actually handle this complex kth power in a fairly simple manner. Even this, I realize, this notation like this is very convenient for equivalence classes. So if you have same I component, the 0 is I component projection, that's an equivalence class. So I'm going to call, if I have one matrix in that R and another matrix in that R, they are equivalent with I projection. So I'm going to call this I projection equivalence and have same I projection. That's a better way to put it. This one is same AB projection. And that's we're going to describe like this. That's an equivalence relation. So that's defined like that. So I'm actually entering this Cayley-Hamilton theorem again to get a more relation out of, and then we can use these projection maps nicely. So if you apply Cayley-Hamilton theorem, you have this quadratic, a squared minus 2a. I will leave that actual calculation to you, but that's I've already shown you. So that's going to be simple exercise. That's the characteristic equation for matrix B, which is 0, 1, 2, 3. And we have to handle that A times B and versus B times A. So I consider this nice one, A plus B, which will be matrix with the first term A and common difference 1. So it's 1, 2, 3, 4. I think that's what that is. Then that one has a characteristic polynomial like this. So let's see what we can do about this. So let's look at the first one and second one and figure out what kind of projection we get out of this. Look at here. If you solve this for a squared, that's 2a. So 2a, a is a base member of that R, so it does not have AB component or I component. So both of them here is 0. So I component is 0, AB component is 0. There's nothing in there. If you look at b squared, that's 3b plus 2i, if you move that to the other side. So I component is there. That's I component is 2i. And there's no AB component. B and I, they're the base member, so is a 0. So let's expand this one to figure out I component and AB component of A times B, or actually B times A. A times B is the base member. So if you expand that, you have AB plus 2BA, not 2AB. This is non-commutative. These are matrices. And we're going to reduce the left-hand side right away. If you want I component, think about what I component A squared has. I component is 0. B squared has I component 2i. So that can be replaced with the 2i. And they cancel with this 2i. Then AB is a base member, so I component of this AB is of course 0. That leaves only BA in here, and therefore BA's I component is 0. Right? So this is done like this. It's possible to knowing that is an equivalence relation. And also the equivalence relation behaves nicely with addition and subtraction and scalar multiple. However, if you multiply two matrices, the equivalence relation is not preserved. We can't do like we do with a modular arithmetic. It's because the symbol is same as modular arithmetic symbol. That might give you wrong impression that we can actually multiply both sides and get the same relation out. That's not true. So let's look at AB component, and in here, if this whole thing is the expression, I forgot to actually explain this. What happened to AB? And A and B are base member when you enter I component, these are all treated as a 0, so that's why it's not there. So if you look at AB component, these two things are also 0, and that's also 0. There's no AB component there. So only this one survives. AB is there. A squared, AB component is none. B squared, there's no AB component. So it leaves only A plus A times B plus B times A having a 0 AB component. So if you subtract both sides, you end up at BA. Actually has negative AB, as that's the component part. That's very nice. So summarized here, A squared, B squared, and BA, their I component is like this, and A squared, B squared, BA, and their AB component is like this. So with this 6 rules, we'll be able to kind of qualitatively discuss the shapes of the kth power of the matrices that are in arithmetic progression. We already considered the case P0 and 2a plus 3p satisfying that arithmetic progression condition. So we assume that is not the case and show that if we have this condition, if you raise to some power, you get this arithmetic progression back. It's not possible. That's our goal. Again, and being an arithmetic progression means the matrix is spanned by these two vector A and B. All right, so you raise to a certain power and you get back there, and n is greater than or equal to 1, so that this assumes at least 2 in there. Very nice. So let me reformulate this statement in here. If you raise to n plus 4th power, this can be, because of this rule, it's all about raising to a higher power and all that. So it is the same as showing this I component is 0 and AB component is 0. Then you're left with these two bases. So this this line is equivalent to the this hypothetical condition right here. I think I wasn't quite correct to explain why these two things are equivalent. So let me do that again. If I raise this one to n plus 1st power, then you're going to multiply out. So you will have all sorts of powers of A, all sorts of powers of B, and they're multiplied to each other. But because of the Cayley-Hamilton theorem applied to individual matrix A, individual matrix B, all of them can be reduced to linear in A, linear in B. So as you multiply them out, always you can reduce anything that has a higher power in there by Cayley-Hamilton theorem, not because of this facts about this projection images. By Cayley-Hamilton theorem on A and B, it can be always reduced down to this shape here. AB multiplies and BA multiplies, or all linear in there. So to which I skipped in here the fact that the let me show that again. All right, here it is, that R was span of these 4 matrices. Now I was saying that this is actually a ring. If you multiply all these, you get back in here. That was actually using Cayley-Hamilton theorem again. Everything that is higher power of A, because 2 by 2, back to linear, and any multiplication of higher powers of A and higher powers of B, then they can be reduced down to this shape. So it's not completely obvious, but after you work out a little bit, you believe that it's actually the ring. So let me get back in here. Therefore, this thing is supposed to be in linear combination of 4 things. If it is missing the other 2, that's the same condition as that. Therefore, I claim now with the correct justification that these 2 things are equivalent. All right, so I summarize that. This is what we want to impose. So here's another thing. So go down to 1 power lower so that n can be 1 its smallest. And because of the Cayley-Hamilton theorem, this is already, again, it's a 2 by 2 matrix. If you raise to mth power, it must get back to this linear polynomial in that matrix M. Some extra scalar times that matrix plus identity matrix there. This is a Cayley-Hamilton theorem. So we know this this matrix here looks like this. There's no AB component, and that's the key in here. So let's use that shape and multiply one more copies of AA plus PB. So here it is. That one multiply another copy, but we use that with this different expression like this. Okay? Now we multiply this out using this projection images. So let's consider this one with this condition, an I component. What is the I component we get here? So let's multiply this one out. A multiplied to A squared is I component is none. If you multiply A to B there, A times B is ith component is none because A times B is the base member. B times A is I component is none. B times B, there is non-trivial ith component, so it's 2 py. I think that's what it is. So let me write that down. 2 py ith component, right? And we suppose that actually is 0. There's no I component there, so we have to assume this is 0 because that's our supposition right there. So let's calculate AB component from there. Oh, I forgot to that IA and IB, we don't get any I components. Let's focus on AB component. A, and we hide that. A squared does not have AB component. AB, of course, it does have a AB component. It's AB is what we're looking for. So PX is there. So here's a XP. So B squared does not have AB component. BA has negative AB components. The BA is a negative AY showed up here. And next one is IA. There's no AB component. IB, there's no AB component. So these two conditions is translated now simply to 2BYI being 0 and this scalar times AB 0. So both of the scalar coefficients must be 0. P is not 0. That's our assumption. Therefore, Y is 0. And Y is 0 and XP must be 0. But P is not 0. Therefore, X must be 0. So we conclude that Y is 0 and X is 0. So if we go back to this statement, that means Y is 0 and X is 0. So you get that nth power of that matrix M. If it is higher power, it's back in the arithmetic progression. That nth power must be identity matrix times the scalar. So that's a pretty strong condition. So this probably contradicts something. So we go ahead and play with it a little bit further. So let's write that down. This matrix in arithmetic progression is nth power must be identity matrix times a scalar. So this gives me a polynomial that this M is satisfying. So this one implies that because M satisfies this polynomial, and there's a theorem that is characteristic polynomial must divide that polynomial this matrix is satisfying. This can be seen as an eigenvalue phenomenon. So this thing has two eigenvalues, and if you play with the eigenvalue in here, those eigenvalues must show up here as well. So that's pretty much why this is true. So this divides that, and this polynomial is a special polynomial. So here's the idea. This one has two distinct real roots because this is non-zero. We assume the P is non-zero, and this negative number. So the discriminant of this quadratic polynomial is actually a positive number, so we have two distinct real roots. So is it possible to have two distinct real roots? If you think about the possibility of n greater than or equal to 1, n must be even, otherwise it's going to always have only one real root, and if it is even number greater than or equal to 2, then it always has two real roots. Those are namely nth root of positive nth root of z and negative nth root of z. So this is a monic polynomial, and that's monic polynomial, has two roots, and it has two roots, must be exactly the same correspondence here. So if you consider this quadratic polynomial with the two roots, and that polynomial generated out of those two roots must be exactly equal. It's a Mani polynomial with the same roots, quadratic polynomial, they must be the same polynomial. But if you expand this one, you get constant term 0 because it's opposite sign. So that forces 2a plus 3p being 0. But we assume that 2a plus 3p is not equal to 0, so that cannot happen. So this matrix raised to the nth power cannot be an identity scalar multiple of identity matrix, therefore this can't happen. So what we have shown so far is that we discovered these two matrices and show that no other matrices will have that property. Thank you for watching. I hope you enjoyed it.